Hello everyone, welcome back to ptet.chemistry channel. So this is a topical multiple choice question on the Cambridge International curriculum. So this is topic 8, well at least it is topic 8 in my book. It's chemical equilibrium. So we are going to talk about equilibrium a lot. You can find some of my shorter concept tutorial videos on the A-level concept tutorial playlist under equilibrium, where you can find more details on what kind of things they usually ask, alright? Whereas here I'll be focusing on the MCQs, but I'll be going through concepts here and there that might be useful to you or someone you know. So do share them if you think it'll be useful to other people. Alright, so when we talk about the units on the Kc expression, in general we say that solids have a unity concentration, meaning to say that we don't simply say it has zero concentration, because then it will invalidate your calculation. It will make your calculation or your expression look like nonsense. Okay, so we use square bracket for concentration. It's raised to the power of 1 because in the balance equation there's 1 there, and in front of the H2 there's 1 there, so we raise it the concentration. We express it as a square bracket to the power of 1, which we don't show. And then obviously the carbon solid I do not show in my expression, simply because it's taken already as a concentration of unity and 1, and we don't simply include it. Okay, we don't include it in our expression, and because we don't include it in our expression, it will not contribute units to our expression at all. So if I just work out based on what we have from our expression, the units are going to cancel out to give me mole per dm cube. Alright, so for the second one, all of them are liquid. All of them are to the power of 1 because it's just 1 in front of them. If I write down the expression, this is a formation of ester, which you would have done towards the end of your O-level or your GCSE. Is about forming the ester linkage from an alcohol and a carboxylic acid. So all of these are the concentration raised to the power of 1. So on the top bit you have mole per dm cube times mole per dm cube, so mole per dm cube square. At the bottom bit there you have mole per dm cube times mole per dm cube. Again, they all cancel out, leaving you something called no unit. They also have another name, it's called dimensionless. That's because they have no unit. Alright, I'm just going to write down the expression of Kc for the third and the fourth one, because for the third one is a very interesting observation. Most people, they will remember about this, you see. So CuNH3 4. Okay, usually we will have a 2 plus for the charge of a transition metal complex, but when they put a charge there, they forgot that a big square bracket must be outside the charge in order to show it as concentration. This will become more important in your A2 chemistry under transition metal chemistry. Here to the power of 4 because there's 4 NH3 there. So going through multiple choice is a really great exercise for you to practice your skills that will be asked throughout your theory paper. Power of 1 times power of 5, mole per dm cube to the power of 5, okay? Because 1 plus 4 is 5. So 1 whole unit there and 4 there. So I hope you can see that comes down to mole minus 4 dm plus 12. So it's not as easy as the other one, but again it comes down to indices and your use of mathematical expression. Yeah. So next one is NO2 and N2O4. So Kc is NO2 to the power of 2, N2O4 to the power of 1. N2O4 square bracket to the power of 1. So this unit is again fairly simple. So there's two of that mole per dm cube on top. I can cross out one whole lot. My unit is just going to be left with mole per dm cube. Alright. In this next question, this looks like an algebraic kind of questions. So we started with B mole of Hi. So I think what I would do is I will rewrite the equation here so that I can, label my initial mole, my equilibrium mole, as well as my equilibrium, well, think about the change in the mole. Okay, so we're gonna have our initial mole or mole at the start, and then what do we have? We have B mole of these, and we have 0 mole of H2 and I2, And then we have the mole at equilibrium, or we call just equilibrium mole. We have X mole had dissociated. Dissociated means it had broken down into this H2 and I2. So X mole had reacted, X mole had dissociated. Started with B mole, so you're going to end up with B minus X. From this equation, 2 mole of HI reacts to give you 1 mole of H2 and 1 mole of I2. So I can think about the mole of H2 formed over the mole of HI reacted, or you can think about HI dissociated. From the balance equation, 1 mole of H2 comes from 2 mole of HI, 1 mole of H2 formed from 2 mole of HI that get dissociated. And then this is equal to, I don't know how many mole of H2 had been formed, so this is just mole of H2 divided by the actual mole of HI reacted, which is X mole, which is why you're left with B minus X, because X mole of HI had dissociated, so there's X. So therefore, the mole of H2 formed is going to be, you move up the X to the other side, you're going to get X over 2. So we get 0 plus X over 2 give you X over 2. If you form 1 mole of H2, you also form 1 mole of, if you form 1 mole of H2, you also form 1 mole of I2. If you form X over 2 mole of H2, you also form X over 2 mole of I2. This equation is for Kp, so Kp is a bit tricky because now you have to total up the mole at equilibrium. So total mole at equilibrium is going to be B minus X plus X over 2 plus X over 2. So half X plus half X is going to give you 1X. 1 of X minus 1 of X is just going to cancel out the X. It's just going to give you B. Therefore, you get the mole fraction. So mole fraction is going to be your mole at equilibrium. So B minus X divided by the total mole at equilibrium. And do we have the total pressure? Yes, we do. Under pressure P here. So that is multiplied by P. And then there's X over 2 divided by B multiplied by P. And then there's X over 2 divided by the total mole, which is B at equilibrium. And there's P. I can simplify this, obviously. So B minus X, P over B. And then X over 2B. And there's XP time, well, XP over 2B. There's XP over 2B there. So that is going to be my mole fraction. Well, actually, there's not going to be by mole fraction. There's already partial pressure down there. So this partial pressure, I've just multiplied by the total pressure there. We need partial pressure for Kp and not just mole fraction. So be aware that sometimes your total pressure don't cancel out, but I believe here they do. If you look at the expression, so Kp is going to be partial pressure of H2 to the power of 1, partial pressure of I2 to the power of 1, because the mole in front is just 1 and 1. So that's the power to which you rest the partial pressure to. The partial pressure of Hi is square because you have a 2 in front of Hi there. So what you're going to do is, I'm just going to put in my expressions, which I've already gotten. So partial pressure of H2. So H2 was the second one. So there was Xp over 2B multiplied by Xp over 2B divided by B minus X and then P over B, and I square it because there's square there, so they become square throughout. If I just write down everything, so there's X squared P squared over 4B squared, and then because you have divided by a fraction, so I'm just going to multiply, use a dot there. The B square is going to come up, and then the B minus X square, and then P square, because it's like when you are doing primary school mathematics, A over B divided by C over D is equal to A over B times D over C. So these are your primary school mathematics. I've just inverted the B square and the B minus XP, both of them square to the bottom thing there. So what happened then is, I can see my B square and my B square cancel out. My P square, my pressure cancel out. So in reality, my Kp is not dependent on the pressure at all. I have a 4, do not forget the 4. There's a 4 there. And I have B minus X squared. So based on this expression, which you could be asked in the theory paper, that is just going to be option D there. So option D must be the answer based on what we had just obtained. Instead of just looking through the options, we work it out as we would have in a structured component. So in this question 3, they're just asking for what is the correct expression. So if I have that, I don't want to rewrite the equation, so I'll just work from there. So mole at start, I have 0.20 mole of H2, 0.15 mole of iodine, so no product. And then the molar equilibrium, I have 0.26 mole of HI. So how much HI have I produced? I have produced 0.26 mole of HI. So just now, previous question show you how much of the reactant dissociate. Here they show you how much product has been formed. Okay. So if I work out the mole of H2 reacted over the mole of HI formed, there's 1/2 from the balance equation. 1 mole of H2 reacted to form you 2 mole of HI. So how much mole of H2 actually reacted? Okay, and how much of HI actually formed? 0.26, because you form 0.26 mole of HI. You start with nothing and you end up with 0.26 mole of HI. That means 0.26 mole of HI has reacted. So the mole of H2 actually reacted is 0.26/2, which is 0.13. You started with 0.20 mole. You reacted 0.13 mole. So you need to take away 0.13 mole. You are going to have 0.07 mole left at equilibrium. Okay. So if I do this for the iodine as well, so the mole of I2 reacted over the mole of HI formed is also 1/2 from your balance equation. 1 mole of I2 give you 2 mole of HI. 1 mole of I2 give you 2 mole of HI. So pretty straightforward there. How much of HI actually get formed? 0.26. Therefore, you can work out the actual mole of I2 reacted. Okay, so that is also going to be 0.13 mole. So started with 0.15, then you react 0.13 mole, you're going to left with 0.02. So your Kc is going to be the concentration of HI squared, because you have a 2 in front of the HI, and then the H2 concentration, the I2 concentration, both of which raised to the power of 1. So this is what I'm going to have as an expression, just like in any theory paper. So that's going to be 0.26 squared, 0.07, 0.02. Okay, a few bits and pieces. They confuse you with the 2 because some students would think, 2 times, so they do that. Okay, and then some students don't know the difference between what is the meaning of the 2 in front. They'll do that and they'll do the square as well. And then this is probably the one where they say you work out 0.13 mole reacts, but you thought that 0.13 goes into the molar equilibrium, and that is a very common misconception and a very common mistake. So you gotta know not to fall into that trap. Yeah, what is left at equilibrium is after how much you have reacted, and then you have whatever is left at equilibrium. All right. So not the easiest thing in the world. Yeah. Part 4 is about Le Chatelier principle. So what would your system equilibrium do in order to return back to equilibrium when you apply a change? Yeah, you want to favor V2 plus. So that means you want to favor backward reaction. You want the equilibrium to shift to the left. Okay, what happened with adding an acid? That means you increase the concentration of H plus. What will the H plus do? Neutralize more OH minus. H plus plus OH minus give you water, right? So what happened is when H plus increase, the OH minus will decrease. What will this equilibrium do to counteract this? So equilibrium will try to increase the concentration of OH minus. It will shift to the right hand side. This is not what you want. You want it to shift to the left. All right. How about B? If you precipitate V3 plus, if we precipitate V3 plus, that means V3 plus aqueous concentration will go down because it will come out as a solid. It will precipitate out. That means it is no longer aqueous. That means the concentration of the V3 plus aqueous will decrease. You see? Okay, so when you decrease this concentration, what will the equilibrium do? Equilibrium will try to increase the concentration of V3 plus, again, it will shift to the right hand side. So B is not what you want. All right. Does it produce hydrogen? Oh yeah, it does produce hydrogen. Okay. So C, if the hydrogen allows to escape, if you allow the hydrogen to escape, that means the concentration of H2 will go down. Okay. So H2 goes down. What will the equilibrium do? The equilibrium will try to produce more hydrogen to try and increase the concentration of hydrogen at equilibrium. Again, it will shift to the right hand side, which only means the only option must be D. And let's think about it. If you make it more alkaline, then OH minus concentration will increase. What would the equilibrium do? The equilibrium tries to decrease the concentration of OH minus, because the equilibrium will counteract your change in order to return back to equilibrium. How would it decrease the concentration of OH minus? It will react the OH minus more. It will shift to the left hand side, and therefore you will favor the V2 plus. Okay, so there's just the application of Le Chatelier principle based on concentration changes. Right? Should be able to explain that fully in the theory paper. Yeah. So this is just a reaction between two gases. Okay, and they are in equilibrium. And the percentage yield is shown according to the various pressure and various temperature. So what can you see? The yield increases. The yield of Z increases as temperature decrease. So as temperature decrease, so meaning temperature increase, it will favor backward reaction, because as temperature increase, you get lesser Z. All right. How about pressure? As pressure increase, okay, so that's how you work out this kind of reaction, this kind of graph. Yeah? On your x-axis, as pressure increase, your yield of Z increases. You can see the y-axis continuously increase as your x-axis increases. Yeah. So that means you favor forward reaction as pressure increase. All right. So temperature is the only one that can change equilibrium constant. When temperature decrease, you get more product. Remember, Z is the right hand side, so Z is the product. Okay, so that means the yield of Z increase as temperature decrease. So your Kc increase, your Kp will also increase. Any of your equilibrium constant will increase because you get more product as the temperature changes. Yeah, decreasing temperature decrease the value of equilibrium constant. This is the word that is wrong. It will increase because decreasing temperature increases the yield of the product. You see, decreasing temperature, you get more product. Reading the graph, okay? Which of the following is correct? Decrease temperature, increase the rate. That is wrong, because when you temperature decrease, your rate always decrease, yeah? Because of collision frequency, because of how much kinetic energy your reacting particle will have. Okay, so all about those things. Increase pressure, increase equilibrium constant. That is wrong. Only temperature can change Kc or Kp or any equilibrium constant. So changing pressure will not change the value of equilibrium constant. So which means that your only option must be D. And let's check whether it makes sense or not. The reaction is exothermic in the forward direction. So I'm looking at temperature. If the forward reaction is exothermic, okay, when temperature increases, your reaction will release less heat because you want to counteract the change. Okay, your reaction will release less heat, therefore it will favor backward reaction. So as temperature increase, it will favor backward reaction. That is entirely correct. Okay, so this is the last question in this 5-question series. Catch me in more videos on these multiple choice tutorials, and yeah, if you enjoy these videos, so subscribe to the ptet.chemistry YouTube channel, like the video, and then share them widely with your network of friends and your students. Okay, thank you for watching.